And our next speakers are from Google, Xingyu and Martijn Bogaard, presenting Dirty Ptrace. They'll reveal how undocumented kernel behaviors can be turned into powerful primitives for privilege escalation and sandbox escape. Please welcome Xingyu and Martijn on the stage.
Hello, everyone. Thanks for being here today. My name is Xingyu, and here's my colleague Martijn, and we both from the Android team. Today we're going to talk about the map-related bugs. I think we were going to talk about a series of known issues about the driver mmap issue, and also I would say interesting vulnerability class. We called it as Dirty Ptrace, as it could override read-only memory in some very special contexts. This talk is also a review of the challenges in securing driver mmap vulnerabilities. So, as the Android team, our mission is to protect Android ecosystem through offensive efforts, and we work on multiple engagement issues, performing vulnerability research, and exploit development. And here's our agenda today. For the first part, we would like to review the known driver mmap issues, including an Samsung Exynos in the white driver 0-day last year. For the second part, we will introduce how the Dirty Ptrace actually works and its impacts on the NVIDIA and also the image tag GPUs on the Pixel 10. And finally, we will discuss how to exploit these vulnerabilities on the Pixel 10, and we will present a live demo for rooting the Pixel 10. Well, so in the Android early years, between 2011 or maybe 2015, I guess, people called it as the golden age of the Android routing. It's very easy for you to download and routing applications and press a few buttons and then, hey, you root your device. It's pretty easy at that time, and most of bugs in the past are like driver mmap issue, because these bugs can allow you to read or write arbitrary physical memory of your device. Like, for example, in the past, maybe 10 years ago, like there's a bunch of memory drivers in the past directly exposed to the on-premise users. There's no SLinux in the past for like 15 years ago. So applications can just like open this driver and like write these drivers, and you basically can read and write all your physical memory. So the routing is very easy. And also, if you mmap the driver memory, it could also have the information leak issue, because if you like the kernel drivers share the same page with the user space, and the kernel drivers like the binder in the past could also write the kernel objects with the kernel address, then the mmap could also lead to the information leak. But in general, exploiting this bug are pretty easy, like, reading kernel symbols, patch kernel functions, and then, you have rooted your device. So for the past decades, maybe 10 years or 15 years, Android was all flooded with all sorts of these bugs, and someone really wants to put a stop to this hacking spree, because like we can't have like so many, kind of these easy driver bugs exist in the ecosystem. So like, for example, for years, the SLinux was introduced and gradually enforced, so users are unlikely to access a number of drivers, and people start sanitizing user input. Like, although the OEM start sanitizing user input, especially for the the mmap arguments like the memory size, the page offset arguments, it's really easy to go wrong, because, like, for example, if you are checking the page offset and the memory size, a lot of developers just simply adds the page offset and size, and it's very to lead to the integer overflow and bypass the security check. Well, so it's 2025. Does the Linux kernel free from the straightforward memory corruption nowadays? Unfortunately, the answer is no, because, for example, in 2023, the BFS lab discovered an off-by-one issue in a driver in the Linux mainstream, and there is another off-by-one issue in the CMA heap buffer, which is used by the Linux kernel and also the Android devices like Android TV, for instance. And both of vulnerabilities just very straightforward. It's like there's an off-by-one here. If you have if the page offset equals to the number of page. So when the fault handler is triggered, then this Linux kernel driver will say, I'm going to install the off-by-one page to the user with read and write permission. So to exploit, you can just map libc memory as an off-by-one page. So you can easily override the libc memories. And unfortunately, this is still the state of the Linux kernel mainstream nowadays. And besides of these memory corruptions we discussed, the mmap memory pages are like very difficult to manage. Like, when we have the driver mapped to the pages to the user space, these memory areas has a special flag called PF mmap flag. So this flag basically means like the Linux kernel is not going to manage these pages at all. For example, like for the reference count, it's all the driver's responsibility to take care of these memory pages. And of course, it's very easy to go wrong. Like, for example, last year, there's Samsung zeroed in the wild about the reference count issues about these special driver mapped pages. So last year, Clem and I from the Google Threat Analysis team, we spot a very unusual binary as part of an in-the-wild exploit chain. So the exploit targets at the Samsung Exynos drivers for JPEG image decoding and scaling. The exploit chain is able to execute object code in the init process, and the exploit behavior is different based on the Samsung kernel versions. Like, for example, if the kernel major version is 4, then the exploit will change its name as the the camera HAL process name for anti-forensic purposes, and interact with drivers and exploit the 0-day. Well, if the kernel major version is 5, the exploit will drop and mount an image file and load the kernel rootkit driver. We will talk more about these details at the end of this talk. So the way how the driver works is that user space has to import user pages as the input and output memory to the drivers. Like, for example, you can specify the type of the input as the user pointers. You can supply all sorts of the user space memory to the drivers as the input page. And also, like, you also can import a bunch of user pages as the output pages. Besides, you also have to specify, like the formats and commands of the JPEG stuff. And once all the initialization is finished, users can ask the driver to kick the firmware for computations and write the output data back to the input data. So a brief overview of how the things actually happens is that once users import the user space pages, the Samsung Exynos IOMMU will tries to map these user space pages to the IOMMU. So you have the input IO pages and also the output IO pages. So what's going on? The problem lies in the Exynos MMU function, because in general, it does not expect to import PFM memory. Like, if you take a look at this code, it will say, hey, if you import a normal memory, that is the non-PFM memory, then the Exynos driver is happy to increment the reference count for that page. But if you import a PFM page, then the driver will basically does nothing. Like, the function here with the mk underscore something does not actually increment the reference count at all, because like the Samsung sysmmu function may think it's driver's responsibility to manage these reference counts, so it does nothing about the reference count. But here's the issue: is that what if someone imports a PFM memory from the device driver and import these pages to the Exynos drivers, set up the IOMMU, and then the exploits can unmap these pages, so these pages are getting freed, and IOMMU actually mapping the freed physical memory. Here is the overview of the exploit. First, the exploit imports the pages from the ION drivers, and because ION drivers, of course, maps the PFM memory pages. Second, the sysMMU function does not increment the reference count when setting up the IOMMU. And third, the exploit unmaps the ION pages in the meantime. So when the IOMMU is set up, you effectively have an IO virtual page mapped to a free physical page. So when the firmware is doing all sorts of computations and send the data back to the output page, the drivers will write the data back to the input page, but the input page already being freed by the exploit. So you have the IO page user-free right here. Also, the exploit writers, they figure out how to interact with the drivers so they can control the exact data sent back to the input IO page. But as we know, the user space program had to send really a bunch of pages to the drivers, and the exploit hope the drivers can free the PFM memory in the right timing, because if the exploits unmaps the pages too early, then the driver will say, hey, this memory does not exist, and it might reboot. So, well, the exploit writer, they have to figure out a way to find the right timing to free these PFM map pages. So the answer is to use the minicall syscall, because this syscall could check like whether you have a physical memory back in terms of mapped virtual pages. For example, if you like have a normal memory mappings, you know the underlying physical memories are not actually backed unless these pages are being accessed. The exploit can cause minicall for its neighboring normal memory. So when the minicall says, hey, the neighboring memory, they have the physical memory backup, that means the IOMMU has already set up the mapping, because the IOMMU eventually has to access to these pages. So the exploit know that this is the right timing to free this PFM memory. So there will be more chance for the exploit to write the user-free IO pages. The exploit flow is pretty straightforward. The page use after-free write primitive allow the exploit to split page tables and use the write primitive to craft malicious page table, and eventually as a user space program you can read and write the kernel code. So that's all the things about the 0-day. Before we dive into the dirty Ptrace, I would like to address that securing the mmap driver code is indeed very difficult by a few slides. Like, for example, there could be a risk condition here about the kernel mmap lock. Like, in the past, when you free VMA, the kernel holds the writer lock. But since the kernel 4.20, kernel now use the reader lock when you free the VMA. So the binder driver in the past have issue like the binder used the reader lock for iterating all the VMA, but the higher version of the kernel now use the writer lock to destroy the VMA. So you have the risk condition here and cause it user free. The VM flag is also very important. For example, if the VMIO flag is not present, then someone can use advanced syscalls to do some really weird things to the VMA and cause all sorts of undefined behaviors. The GPU page user free for sure is also very popular vulnerability class, and I'm not going to talk more about the details about that because we already have some great talk here in the POC. The GPU itself has very, very complex logic, so you could have like map the CPU mapping of the GPUs by the mmap, and eventually you can interact with the drivers and access to the free physical pages. So finally, if you unmap a read-only pages to the drivers, it doesn't really necessarily mean these pages are read-only, because if you look at the kernel code, the kernel will clear the VM red flag, but the VM main red flag is not cleared. That means if you create a read-only page for the drivers, and you might call the in-product syscall to make the read-only writable again. So, well, as you can see, writing secure driver mmap code is very difficult sometimes, and there are also some like techniques that are not pretty much well known that could override the read-only memory. Well, so let's talk about the Ptrace. First of all, I would like to ask a few questions, like if you have an unprivileged debugger tries to write on the read-only memory, if the memory is mapped by the map private, can you write on this read-only memory? And second, if you have the read-only memory mapped by the map shared, can you use the Ptrace to override this read-only memory? So for the first question, the answer is yes, because the kernel will check like, hey, this is a private flag, and the kernel is eventually will allow the Ptrace to override the read-only memories and trigger the copy and write along the way. However, of course, you cannot overwrite the map shared memory, because otherwise you can just import a libc and attach it by the Ptrace and override the libc memory from the unprivileged user. So are there any exceptions? So what happens if you interact with the drivers and map the memories from the drivers with the VM PFN flag? Can you use the Ptrace syscall to attach these memory pages? So well, by default, you cannot use Ptrace to access to these PFN pages. And if you look at the access callback, you can the argument is pretty clear. Like, hey, you have the kernel VM pointers, you have the user space address, you have the buffer to read and write. If you look at the last arguments, Linux kernel basically said like, hey, if the write here is 1, that means someone wants to write the memory, and if the write is 0, then someone wants to read the memory, and that's all. So we check a lot of open source code, and people implement access in this way. Is very straightforward. Like if someone wants to write, then we just write the buffer to these kernel pages, and vice versa. So what can possibly go wrong? If we check out how the Linux kernel handles the Ptrace syscall, then we can, when we exit Ptrace to overwrite memory, the Linux kernel will basically call the write int, and eventually call a bunch of functions called access remote VM function. And this function calls another function for conducting all sorts of security checks. Like, for example, this is the function to make sure you cannot overwrite the read-only shared memory. But there are also some exceptions, because this function will refuse to conduct any security check if you have the memory mapped by the drivers. It will just basically return an error to the callers without actually doing anything. But the Linux kernel also gave the Ptrace a second chance, is that if the driver register the access callback, it will invoke this callback. But here is the issue. Well, this configuration is always enabled, and Linux kernel basically does nothing to check about these arguments. And if you check out the Linux kernel documentations, it basically says like, hey, this call is kind of the access callback is used to handle very special cases. And the callback is only needed if you want a debugger to attach to this typical VMA. But from the driver developer point of view, they have no idea kernel does not sanitize these arguments at all. Like if someone wants to use the Ptrace to write on this read-only memory, the driver developer may say like kernel must have conduct a security check to make sure these pages are not writable. But the Linux kernel people assume the drivers will check the write arguments because they think it's better to pass the bug back to the driver. And when we fire back to the NVIDIA's and also the image tag GPUs, they believe we should fix the issues in the Linux kernel mainstream, because they want the mainstream kernel to check the page property, like can we really write to this page But the kernel folks think we should talk to the driver developer because it's their fault in not sanitizing all the user input. So it's sort of the blame game. And what's more, what kind of security impact you could have by overwriting the read-only memory mapped by the drivers. So the drivers, like the GPU, TPU, they may allow user to import memories, and depending on exact memory mappings policies, you may remap the memory back to the user if possible. And some drivers, like NVIDIA driver, they may also map read-only privileged memory back to the user space. For the GPU, it's very common that GPU has the features to importing the textured memory from the CPUs to the CPUs, and the GPU drivers will eventually map these pages to the GPU. And historically, these features are very easy to go wrong because there's a lot of bugs. You can import libc memory to the GPU drivers, and GPU drivers is happy to overwrite all sorts of the read-only pages. After we discussing with the Project Zero team and also the Android kernel teams, we have proposed a kernel change to the mainstream to the Linux kernel mainstream. The patch here is actually very simple because for the Linux kernel, you can check if this driver mmap page is readable or not. But we got already a lot of questions from the Linux kernel community. Like some people may think like, hey, this is really uncommon scenario. What's your security impact? Some people will say like, hey, we think only root user can call the Ptrace, so your patch doesn't really solve anything. Or some people will say this is just a debugging features and it's not the Linux kernel's responsibility in checking all the input arguments. So we conduct security reviews on the open source GPU drivers, and we found several security issues. First, for the NVIDIA GPU, you can surely talk to the NVIDIA GPUs, and NVIDIA GPUs has implemented functions for checking what kind of protection bit the NVIDIA GPU should give to the user space program. And for sure, it says if you are the root user, then you can read and write on all sorts of the memory. But if you're not a root user, the NVIDIA GPU drivers will check the memory policies and return calculated protection bits back to the callers. So if you are an unprivileged user, users can map the PCIe bar memory. And the driver only allows the unprivileged user to map the bar memory with the read-only permission. The NVIDIA driver also implement the access callback without checking the writability. So basically, if you can just use Ptrace to write the read-only memories, and in fact, you can write on the PCIe bar memory for the NVIDIA GPU. What happens if you can write the read-only bar memory? Because we know the CPUs can access to the bar memories, maybe bar 0 or bar 2 in some very specific GPU memory context. It can access to the MMO registers. It might access to the VRAM. It might also has the impact on the NVIDIA DMU engine. The patch is really simple here, is to just check if this page is readable or not. So NVIDIA classified this bug as confused deputies, and we also check other GPUs whether they have implemented the access callback. So the AMD, Intel, and ImageTech GPU, they implement the access callback. Intel, for the Intel GPU, there's no security impact because they managed to implement the access callback in a correct manner, because they do check that this object is readable. Is read-only or maybe read and write. And for the AMD GPU, there's also no security impact, although the AMD developers do not seem to realize it's impossible to use Ptrace to override the read-only memory. The AMD GPU has memory mapping policies to disallow the AMD drivers to remap memory to the CPU if the memory is originally from the user space. Well, in other words, like there is no legitimate reason for user to import memory and remap the same memory back to the user. So safer GPU memory mapping policies prevents this unforeseen attack. But for the image tag GPUs on the Pixel 10, it's a different story. First, the image tag GPU maps out several read-only memory back to the users, like the NVIDIA drivers. It could map the shared read-only driver information page. It could also have a shared shader memory pages, which is accessible by all the Android graphic process. For example, like the shader memories originated from the GPU firmware and it's read-only. So what happens is that you can, of course, use the Ptrace to override these shared shader memories, and you can cause memory corruptions because all the Android graphic process, they trust these read-only memories and they have zero sanitizations on its metadata, so you can corrupt all sort of out-of-bound access in different Android process. Like, for example, this is the crash dump of the Android UI process. The image GPU, well, on Pixel 10, also implement the functionalities to import user memory. So effectively, you can import any read-only file to these GPUs, and you can use the Ptrace to write this data, to write on the read-only memory. So, well, now let's welcome Martijn for introducing the DXT GPUs on Pixel 10 and demonstrate how to exploit this vulnerability on Pixel 10. Thank you.
Okay, Xingyu, thank you for giving, I think, a very nice overview of the different vulnerabilities. Let's now start to focus on a more practical case. And before we can do that, we need to go first a little bit in how the GPU on the new Google Pixel 10 works. Because one of the changes of this year is moving to a PowerVR DXT GPU. So how does the driver stack of this new GPU look like? So we start with our Android application. And the Android application wants to do some rendering job on the GPU. And to do that, it will interact with the user mode driver stack. And this is where OpenGL, OpenCL, and the Vulkan stacks are being implemented. This user mode drivers will then interact with the kernel driver. This is a quite big driver, but one of the main components inside the kernel driver is something called the bridge server. This is effectively an ioctl that exposes 100 to 150 different commands for working with the GPU. And the user mode stack calls into this bridge server to invoke the functionality it wants to use. And then when you have done your configuration, the kernel driver will submit the work job to the GPU. This bridge server organizes the commands it exposes in different bridges. So we have, for example, the server core, which is like getting version information, hardware capabilities, mapping the shared information pages, shaders, but also a memory management bridge, a cache management bridge, debug information, and several other bridges. And besides the generic bridges, we also have bridges that map to specific hardware components within the GPU. For example, there is a 3D rendering bridge, but there is also, for example, a bridge for compute workloads for the GPU, and also several hardware synchronization primitives. So how do we actually interact with the GPU? So I would like to give you an introduction that is very simplified, the steps for rendering something on the GPU. And it starts with creating a device memory context. This is effectively the context to which all memory will get attached that will get mapped into the GPU. And as part of the device memory context, there are several device memory heaps that are being created. These are effectively pools of the GPU addresses that we will will then later assign to the memory that we are going to map inside the GPU. Then we can actually start allocating memory that we want to use as part of our rendering job. This is done with a command which is called physical mem new RAM-backed PMR. And PMR is a physical memory resource. Also there, as part of a standard rendering job, you can have tens, if not hundreds, of memory regions that will get mapped in the GPU. However, there is also a call that if you don't want to allocate new memory, we can actually map an existing memory region from our virtual address space inside the application using the physmem wrap external memory call. Then we can actually connect the memory we have allocated with regions inside the GPU by mapping it using the devmem internal reserve range and map PMR call. This is effectively the mmap for the GPU. Also there, we can do this many times. After preparing the memory, it is time to start creating a rendering context. This is where all the information about the rendering job is getting attached to. And besides the rendering context itself, we need to prepare several data structures that are used by the kernel driver and the hardware for managing the rendering job. One of them is the so-called free list, and the other is the HWRT2 dataset. This is used in the background. And when our rendering job is ready, we can actually send it to the GPU hardware with the kick command, and then the GPU hardware will start doing its work. We can do as part of one we can do this many times, but when we are finished, of course, we need to clean up and release all the resources that got allocated. But this physical mem wrap external memory is the one that deserves extra attention. Because what we do is we give it a virtual address, a size, and some flags on how we want to import this memory inside the GPU. And we do the ioctl to the bridge server. The bridge server will prepare the PMR wrapping this memory, and it will return the handle to the memory region we have now wrapped. This is a PMR handle. We can then use the PMR handle both connecting it with a GPU virtual address, but we can also use mmap to map it back inside our address space of our application. The flags are specified what the memory permissions are for the memory we are importing. We can, for example, say if it should be readable or writable by the CPU, and if it should be readable or writable by the GPU. Currently, it is not allowed to import memory writable in the GPU to prevent memory overwriting issues. So it is only possible to import existing memory as read-only. So how can we connect this with the vulnerabilities Xingyu has been presenting? And how can we actually turn this into an attack? So we start with our application. And the first thing we do is we fork. So we have the application process itself and we have our child process. And the parent process for now will just keep waiting until we are ready within the child process preparing the memory for the attack. So what we can then do in the child process is open a file that is read-only and that we want to overwrite. And we map this file inside our address space as shared read-only. But then we use this physmem wrap external memory call, and we map this read-only file as read-only inside the GPU. And then we use the handle we get back from the GPU driver to create a second mapping, again shared read-only, with the same underlying memory pages, but with a second virtual allocation in our address space. And then we say back to the parent process, okay, I want to be debugged, please take it over for now. The parent process is like, okay, the child is ready, and it can now use the Ptrace POC data to use with the virtual address of the second mapping to now write to that memory region and thus the underlying memory of our read-only file that we have mapped in our address space, allowing us to overwrite files to which you only have read-only access. Any file can be overwritten this way. So how can we use this to get root? Well, there are all kinds of interesting targets to overwrite, right? We have all kinds of shared libraries, we have system binaries, but we want something that is highly privileged. And of course, Dirty Pipe has already demonstrated init is the perfect target for these type of attacks, so we also do the same. And inside init, we have a very interesting piece of code, which is the property service thread. This is effectively the piece of code that keeps running as part of init, waiting if system properties get changed and if the init scripts have attached behavior to changing these properties that should get executed. And then, as part of this polling loop, it detects a property has changed. It will call the should-log function inside libbase to see if it should actually write a log message that it is actually going to do something. From applications, Android applications nowadays, you don't have direct access to the system binary anymore. So you cannot directly overwrite init. However, because the init binary uses should-log from libbase, and we have read access to libbase, what we can do is actually write our payload to the libbase shared object and use that to get code execution within init. So, well, that should be pretty trivial, right? Because init runs as root, so just overwriting libbase should be enough. Well, on modern Android systems, it is not completely that simple anymore. Because also, although init runs as root, right, it's not unconstrained. So our initial idea was, let's get code execution, and we just load a kernel module from init, because, well, as part of the boot process, init can load kernel modules. So let's drop a kernel module somewhere and use it from init, and then we do privilege escalation. Well, easy peasy, we are finished before the end of the day. Well, init itself has no access to the GPU. So although we can get code execution within init, we cannot use it to do anything using this vulnerability from there. But also our application does not have any read access to kernel modules. So we can also not use this vulnerability for dropping our privilege escalation kernel module. So we actually had to come with something more complex than this. And, well, we had this technique that was found in the wild of dropping a disk image. So we decided, let's go down that path. Let's reuse that technique and we bundle disk image as part of our malicious application, drop that somewhere in the file system, and use that to deliver our kernel module. Then, after init mounts our disk image, we use a mob probe to load the kernel module, and then we just do our privilege escalation. However, there is another obstacle, and that is that although this property change listener thread inside init is executing on a regular basis, if the device is not used, it can take a while. When properties change, it's pretty unpredictable. Sometimes it's quite quickly, sometimes it can take quite a while. So we were also looking for, like, what is the easiest way to reliable trigger a property change, and it turns out starting the camera application is actually a 100% guaranteed success of changing a property. So how is our payload going to look like? So this is the initial payload. This is the one that we inject in libbase over the shoot log function. And the first thing it will do is check if we actually run as part of init. Because if it's not init, it's probably not smart to run our exploit code. We should just say, no, don't log, return normally, and ignore this process. If we are in it, we will clone our process, effectively forking it, and in the parent, so the main init process also there, just continue normally. Your work is done, we are finished. But inside this child that we fork from init off, this is where we actually are going to run our second stage payload. So we will resolve the DL-open and DL-sim symbols, open a random system, a random file from the system that applications can read, but also that is accessible by init. Interestingly enough, these are, for example, the fonts. So we just override one of the not so often used fonts and put there our second stage payload as a shared object. Look up its entry point, and we jump to the second stage. So we do it in 2 stages because our initial space is a bit limited, and we are delivering a complete disk image as part of the payload. So this is why we have most of the functionality implemented in the second stage. That we used a font file, you can pretty much use any file that is accessible by init, and that is also readable by Android applications. So for the second stage, we are going to make a mount point for our disk image inside the data partition. We are writing our disk image to the data partition, and also ensure it has the correct SALinux label. Inside our disk image, we have our privilege escalation kernel module, plus some extra files that we need to satisfy mod probe. We mount our disk image using the loop device driver. And again, we fork our process, and this time to switch to the mod probe SALinux context and mod probe the privilege escalation driver. Our privilege escalation driver, it's very simple. It's effectively a peek poke driver, exposing a dev node that allows you to read and write arbitrary physical kernel memory addresses, plus allowing us to look up some of the required kernel symbols. And then finally, we do the standard privilege escalation steps, disabling SALinux, walking the task list, setting ourselves to root, and giving ourselves all capabilities. So I have here a Pixel 10. What's good to know, this vulnerability was found before release, so we actually had to unpatch it for doing this demo. And I am going to try to demonstrate it live for you. So let me rearrange the windows for a moment. Yeah, so standard ADB shell, nothing special. Yeah, you can see my screen. So we implemented as a very basic Android application. I added some sleeps to make it a tiny bit more visual, because otherwise it runs so fast that you literally see nothing. You could see the camera app popping up and disappearing again quickly. Also there we have added like a 1-second sleep to it, so at least you could see it, because otherwise it runs so quickly. SALinux is set to permissive mode, and our ADB shell is root. And yeah, that is effectively our presentation, our talk. If you have questions, please. And otherwise, we are more than happy to discuss. At the end, we will be around. And yeah, thank you, everyone.
So, do you have any questions?
Thanks for a great talk. Small question about your privilege escalation stage. You load the kernel module, and how did you bypass the module signatures, or it is not enabled in Android?
Pixel has no module signatures.
But why?
I don't know. I can only state what the current situation is.
Maybe it is because Android needs the vendors load their modules, and sharing the keys to sign the modules would be problematic.
For example, I can hypothesize there are other reasons, like if you are that far, what does it add, etc. I don't know. We are not really part of that discussion why exactly these things are as it is.
And second question, could you please elaborate about this patch by Jan Horn? Did it fix the whole problem with Ptrace or not?
Okay. Just give me a moment. Yeah, so this is the patch for checking from the Linux kernel to check the page readability, with assuming like you are not actually talking to the driver with the map private flag. Like this assume everyone should use the map shared flag when talking to the driver, and we think that this patch could be sufficient in checking the page readability. If you're using the private flag to map with driver, then you are basically running into issues with the copy on write or something that could make things very difficult. But it's more like we think it's driver's issue if it allows the private mapping.
And did this patch, was it patch applied to upstream, or was it declined by the maintainers?
I think at some points, like a lot of people are very confused, and especially like we talk to the mainstream people, and eventually they think we should talk to the driver people, and driver people think we should talk to mainstream people. So no one has really had the idea like who should check the page readability. But my point of view is like surely the Linux kernel can do that, but I think maybe additional work we have to do with the mainstream people. In my point of view. Thank you.
Thank you very much.
Do we have more questions? Then let's give a big round of applause for our speakers once again, please.